Just the one.
Right.
Okay. Homework due Friday, right? I would like to see a little model write-up, which is part of the notes that I've sent that are out there now. There's like 3 or 4 note sections that I buried those examples that I talked about on Monday, right? We as engineers, right, our way to convey our information is through our calculations, right? That's how we communicate. Obviously, lots of us are not very social individuals, okay? So we're trying to communicate in a way that someone else can pick up these calculations, right, and use them. We'll talk about that in a little bit, but so FEA in the industry, okay? We've talked about this a little bit, but I wanted to kind of consolidate thoughts here so that you guys have this in writing. Yes?
One random question on that homework too. What did you want us to do to verify if we needed second order effects or to track those? Could we just use VA or do you want us to do a hand count?
Hand count.
Okay, so.
It says hand calc in the question. So finite element analysis in the industry. Well, if we look at structural engineering in particular, right, we use these software packages to determine element demands based on structure configuration and loading, right? It's very common to have powerful post-processing capabilities to utilize the finite element results that we get, right, in VA to further even complete the design, right? So really, the finite element analysis method, as you guys did in the exam, right, really stops at getting the force and displacement matrices, right? Those 2 ones in the first problem of problem 20. And it's everything beyond that is just post-processing, right? We're going to use that data, that information, and we're going to use that to our advantage to then, apply it to, in particular with visual analysis, RAM or RISA, we're going to apply it to structural engineering problems, and they're going to do further post-processing so that we can, use that information to design things, right? Figure out what materials or members we're going to use, right? How we design connections, okay? And all of that comes from the finite element method, right? Or analysis that we conduct. There's a lot of software packages now that allow for, and I mentioned this, integration between drafting software and our analysis programs, right? An example would be Visual Analysis has a connector or like a little module that it adds onto it where you can integrate Revit into VA or VA into Revit. What's the problem with this? Well, it's challenging to get this right because drafting is commonly done in a 3D space, right, with a lot of detail. If we go to this guy here, right, this is the Revit model for the Norm Asbjornson Hall, right? There's a lot of shit going on here, right, in Revit, and you expect VA to then you just click a button and it takes everything that's here and it gives you this nice, beautiful model, right? That doesn't happen, okay? I've tried this multiple times. Every time I tried it, I fully regretted it, okay? I wish I would have just started with a VA model, right? Just doing a model, maybe looking at this as references. Obviously, we had grids in here, okay? But you can imagine, like, Revit, as I think I mentioned also, is trying to use to their advantage the idea of, okay, now we can even start before we even generate a VA model, and when you're modeling, will in the background, and they do it in Revit, in the background, they create what's called the analytical model, which is their version of a, 1D, like beam element, line element, right? For every wide flange that you model in here, or member you model in here, it's got an analytical model member element to it, where it has a node and it has a member that connects it, okay? And you can move those things around, you can manipulate them, and you can actually analyze this in Revit. And I think they're trying to get to that point where you no longer even have to move out of this, right, as a structural engineer, and you could design the building inside of Revit.
Have you tried
Fucking
using
cool.
what they have
No,
already?
I mean, I've gone to the extent of like showing it in an effort to try and figure out. We learned in doing it multiple times where we were trying to take this model and push it into VA, is that it was worthwhile to look at the analytical model, because that's what VA comes into Revit, and I'm sure RAM or RISA or some of those other programs. when they create a model from a Revit model, they look at the analytical model in Revit and not this model that we're looking at, right, the three-dimensional one. And so it makes sense to go in here and say, okay, where is my analytical model? And there's ways that you can say align it to center line of beams versus align it to top flange of beams and things like that. Because obviously in this model, right, Norm Asbjornsen Hall, there's all sorts of different sizes of wide flange members in the floors, right? And in VA, all of our members are aligned to the center line of our beam, right? So if we looked at the picture view of the VA model of this, which is actually down here. All right, so this is the structural model part. So you can imagine all of these wide flange members are different depths, right? You got some big ones, little ones, or whatever. And they're all aligned where the top flange is the bottom of the deck, right?
That though, that only like would come into play in the post-processing, right? Like as far as finding like
Well, what I'm saying,
member reactions, you'd still get the same, like.
no, because
Where it's aligned.
well,
it's like
VA
has to
with the,
stress it.
yeah, the problem is that we want line elements to have nodes at the end of them, right? And all of those nodes have to line up between all of the members, right? And so if this member, see these two wide flanges with way different sizes,
Yeah.
right? The analytical model in Revit centers a line element at the center line of this member, right? So the node on the end of this member is lower than the node on the end of this member, right? And if these members aren't aligned, as you can see here, right, this column isn't, breaking this beam, right? It's inside of it. So you got all this alignment issues going on where Revit's analytical model has this line element that's centered on this column, right? But that center line of this column might not line up with this, whereas when we put it in VA, we have to have things connecting at nodes, right? And so we would have to add additional analytical element, like line elements, in order to make this happen in VA. So what would happen is we would take this Revit model, we would try and push it to VA, and then we'd have all of these problems happening, right? All of these nodes at different heights, so then it's like, okay, how do you consider what your story height is, right? Our top of our deck might be 18 feet below the finished floor on the first floor, 16 feet, right? But when we pushed it from Revit to VA, we get like all these nodes that are like fractions of an inch different all over the place, right? And so VA has gotten a little bit better. We worked with Adam and actually Dan Van Lushen on like how they could implement that to make it better, because what they've done now is you can create bands of like story levels, so it takes all of these crazy node heights everywhere and it just smooths them all out, puts them at one level, which is helpful, right?
So surprising that they don't have like a team of coders, or like they're just straight up amateurs coding.
They are amateurs coding, yeah.
That's like so kind of impressive, honestly.
Yeah, I mean, but I don't know that I would consider Adam an amateur coding though. I would he's gonna come, I'm trying to get him to come back in and do some more stories. I really want him to show us some of the code of VA, right? It'd be interesting to see, like, from now you guys have some experience with MATLAB, interesting to see like what they're doing inside of VA. It's like, how do you take a beam, once you have the nodal reactions, right? Then they have to go through and they use mechanics and they calculate at all those little discrete points like you did in your homework, what the internal forces are. Then they have to take those internal forces, relate them back to the AISC, right, the steel manual, and back to all the checks in chapters E and F and G and everything else. Like, what does that look like? I mean, that's impressive.
It's like, I don't think he's been like, I don't know, done any schooling about coding.
No,
Like,
no, I
he's
don't
not
think
really
so.
gone to, like-
Yeah. From like a training standpoint, yeah, I mean, I think they're pretty self-taught.
It's pretty wild.
Yeah.
Is there a nightmare?
I think engineers are pretty well aligned with being coders.
I mean, I feel like coding.
Have you
is-
seen our code?
Yeah, but like you think of it from I mean, like you guys are, I assume you guys are very analytical, right? Very detail-oriented people, right? Like think of things as steps, like you're stepping through
Shit
stuff.
gets deep, bro. Like,
I-
my computer science friends, like, looking at their stuff, it's so bad. My little sister is, like, computer science stuff. It's like, oh, it's like,
way more
But it's
advanced.
just like, I bet I could figure it out if I took the
Exactly.
classes, but you build a lot of classes that have all these like weird techniques and things that are not intuitive to like
Yeah,
do
true.
certain things that you would never think, like
Yeah.
the way Ladine codes, I was like, why would you even like
Yeah,
think about doing that?
Well, that's the thing, although it can be done so many different ways, probably, VA probably not the most efficient code, it's
Yeah,
probably,
maybe.
No, Adam has said that too, like.
probably clunky code,
Da-
but
when
it
it,
works.
yeah, when it first started, like Dan was, Dan Van Lucian was a professor up here at the university, and he started it with a grad student. And then from that, they just kind of left the university and started the whole thing. And so Adam has said multiple times, like equivalent, the energy equivalent forces, we've talked about and you guys have implemented. When I was talking to Adam about it a few weeks ago, he said that it wasn't until I don't know, he said recently that they actually implemented that. And that it was done differently. It was like tributary area and stuff, and it wasn't as accurate as it should have been. So they're always making these little advancements, right?
It seems like really bad.
Right? That's what I thought too, but that's what I thought too. Like, shit, man, don't tell me that.
Do they just really hate when like a new section of code comes out and they have to read through the entire thing to?
I mean, at this point, I think everything's established well enough that it might be some small tweaks, right?
It's
And
probably like a
adjustments.
summary of changes.
Yeah, and it's like, oh shit, they decided on this equation to put a square in there and add an extra term. I'm just gonna add a few things, right? So where was I getting at? I was getting at the fact that, right, it's tough to take from our real world, the model of our drafting model to VA, but we're trying to bridge that gap and it's getting better all the time. And then at some point, I can imagine Revit's gonna say, well, screw RAM, RISA, VA, you guys don't need to do that. You can just do it in Revit, right?
Autodesk will make even more money.
Yep, exactly. You can up their whole
Yeah.
$2,000 a month. I just re-upped my Revit license the other day. It's like $2,500 a year. So it's challenging to get it right. I would, at this point, I haven't had a very good look at it. I would just take and look at the drafting and then make your own model from it. Yes.
I'm kind of confused what you use like such a big model. Like I feel like when I've had little modeling that I've had to do, it's like little parts of things, like one movement frame or like one connection sort of thing.
Yep.
So I don't know what you would do with one model, the entire, like it doesn't just check like everything.
It checks everything. It checks every member.
No.
Yes. Yes, isn't that beautiful? So like in this model, right? So we took A&E's architecture, we took their architectural model, and we started modeling, right? Which I'm sure you have had some experience in Revit now, right, Madison?
I avoid Revit at all costs.
Dude, that you need to embrace it, and the sooner you embrace it, the better off you'll be. I'm going to tell you that right now. Okay? This is the future. All right. Engineering firms that don't use Revit are going to die.
We use Revit, we just don't use it on every project.
Yeah. So we took their model, and inside of it, we created the skeleton, right? And the power of having the skeleton is then we use that. Some side views, right? This is my little baby right here. It's the bridge. I designed the little stairwell that goes onto the parking garage, and then that skywalk that goes across to the building. Special concentric brace frames in one direction and special moment frames in the other. It was a pain in the ass because they didn't want braces in one direction, and I couldn't do it because of the stairwell. Right? Sick. So if you go look at that, don't find anything wrong with it, please. But
What did they end up doing with those giant columns in the front?
they wrapped them, so they're not that big.
I didn't think so.
No, they're not that big. They're just wrapped.
Try to make them.
Because from a perspective,
You know,
they weren't big enough. They would make it look like
It
there
was gonna
wasn't
collapse
enough
on your
there
head
to
as you're
hold the
walking
building
in.
up. Yeah, I mean that's architects can. That's their deal. So anyway, this is the full model. The beauty of having this full model is, Madison, we designed this. I mean, we had two. We had one. This was gravity, and we had one for lateral.
Oh,
And so this one designed all the gravity members in one shot.
like wood and steel, or is it like all steel?
It's all steel. It's all metal.
You didn't like hand
Concrete on
check or
metal
anything,
deck.
you were just like, and then like.
Yeah, we hand checked a few. But that's the
So
beauty
you
of,
do
like
all
for a
gravity members
validation.
in one shot, one model, just like that.
One model, one shot.
What, like, who, like,
All
How'd you
the
permit that? Did you have to go through and graph every single member?
No, I mean, they have like VA has member results, right? And it will relate all of the steel checks, right, in the steel manual. And so it runs down and it gives you a unity check and it'll do combined, everything. And it puts it on one nice little printout. And so usually what you would do is you put VA, we haven't done it yet, you can create design groups, right? You probably mess with that, Aaron, right? So you can like grab as many members as you want, you can put them in a specific group, because the benefit of that and the critical part of doing that is the fact that, these members might be braced differently than these members, right? And in order to check it, and according to AISC 360, the steel manual, you need to know, right, is it continuously braced at the top? Does it need to check lateral torsional buckling? All of those things. Is it braced at the bottom? If it has axial load, what's the K value? Like all of those things. And so you end up picking these, like segmenting these out. You create a nice big key plan that you'd say, okay, this is design group 1 for beams. You'd show that, and then you'd have all these printouts, and you might check a couple to verify that the unity values that they get for checking flexure, right? If you went to section F2, you were doing all the flexure checks for beams, right? There's the yielding, there's lateral torsional buckling in there, all that stuff. Those are verified, and that our model is doing what it should be.
So how long with how many people did that take?
Oh, dude, I wish I should bring in the full calc thing. It's like stacks of notebooks like that thick
Just for
for the whole building.
gravity.
But
No,
it's
for the
like
whole
you were
building.
making that model though, like,
Like weeks.
yeah.
So you just start at the bottom and go.
Start at the bottom and work your way up.
I remember-
And then it's a pain in the ass too, because you look at this thing, and of course, and I was gonna mention it here, is like, you're almost required to do something like this. I mean, you can break it down and simplify it, you can. But, I mean, some of the angles and geometries of today make it really tough to, break things down simply. When you're looking at like larger commercial buildings, right? I mean, you guys probably do a lot of, when you do like multi-family residential, the big 18 plexes and stuff like that, flexible diaphragms. I mean, you can do things by hand
Easier than a house.
very quickly. Yes, it's very quickly. Right, you have all of these joists that you're just like taking 4 units and you're copying them over
Same
like
layout
4 or 5
every
times,
time.
yeah, and then they stack it all on top of each other. And so in that case, yeah, you break it up into like hand calcs and just do it one at a time. Or you'd like break up components and do it in another analysis software like Intercalc or something like that. Do you guys have Intercalc? Yeah.
I remember Morley telling me like any old schmuck could do like the gravity design for a building, but like he's like, we get paid to do the lateral design.
Yeah.
See,
That's
the lateral
funny.
design, I feel like, is so subjective to the person doing it, like how you break it up and how you. feel
Yes,
comfortable
it
doing
is.
It's like there's not a science to it, and there's like.
I mean, there's somewhat of a science
Well,
to
there
it,
is,
right?
but
I
it's
mean,
like, there's still like, you could do, there's like
Physics,
50
right?
different ways to do the same thing.
Yes, for sure. And so, yeah, I mean, and the benefit of this is, like, if you have an architect that's changing stuff, right? Or they wanna like shave some beams, this makes it pretty easy to go through an iterative process instead of like erasing and redoing your hand calcs every time, right? This is like, oh, you wanna change this beam to a W21 because it interferes with a duct. I'm just gonna go in the model, I'm gonna change it, it's gonna change all my calculations, and then I can just print it off once, right? So that they can go to the city and get a permit.
So does it show like when one member fails?
Yeah, so in the design view tab, which we haven't really talked about, we will, is it will highlight members based on their unity values. And so it will, like, they'll show red if they are above 1. So, yeah,
Is unity like the ratio of capacity to demand?
yes. It's demand over capacity. So over 1 is bad, right? And in VA, you can then go a step further, and like, once you have this, in each one of those design groups, you could say, all right, I want to design this, right? You go in with a guess. You could just design it, and you could limit it and say, all right, all of these members, I wanna make sure that they're not deeper than 12 inches, and I wanna make sure that they're wide flange sections. You hit go, it gives you like the top 10 like best members with respect to unity values based on the, bracing that you decided to use and all of the design checks that you gave it. And then you can select it and then implement it and then it dumps it. What?
You want like near 1 is like what you're going for, like
Yes, but there's also,
Depends.
yes, it depends on whether you're looking at, well, you always want it close to 1, but you want for the most efficient design, but there's strength, but there's also serviceability, right? There's deflections you have to take into account. So not only are you going to AISC to look at the strength, but then you're gonna go back to like the IBC and look at deflection requirements, right? And make sure that, you know, should the beam have L over 240, right? The other benefit of doing this is we could use this gravity analysis for like vibrational analysis, because VA will go through and it'll look at your eigenvalue, eigenvector problem, right? It has mass associated with all of these members and things like that. So then you can figure out, okay, what's the natural frequency of this floor? So then you can do a check versus the excitation of people walking or a lab or whether there was, you know, aerobics. I mean, on the 3rd floor of this, because the gyms fell down, they were doing aerobics, right? So that might have influenced other people in other rooms if the floor wasn't looked at for vibration, right? Okay. But another engineering firm, DCI, Sam could have said, fuck that, I'm not gonna do a VA model for that whole thing. I'm just gonna design it all by hand, right? You look at like little chunks, you do a key, I assume,
That'd be huge.
it'd be huge. It would be huge. It'd be an undertaking. Especially because like every bay was a bit different and like the spans were a bit different because the whole building kind of tapers, right? And so it was, yeah, pain in the ass. It would have been a pain in the ass by hand.
It's all architectural.
That was all a rigid diaphragm, wasn't it?
Yeah, everything's concrete. But we never look at it, like, so then that's a thing that you can decide as a designer too, right? The code allows you to make some assumptions. Code allows you to make assumptions whether it's flexible, whether it's rigid, or the power of it, like VA and the finite element analysis, you can really try and match the mathematical model in an effort to try and match the real world, right? Because in the real world, it's not rigid, right? In the real world, it's not flexible, it's somewhere in the middle, right? Somewhere in the middle. And so if you model it with actual plate elements that try to closely mimic the stiffness of the diaphragm, then you're somewhere in the middle and hopefully you're closer to, you know, what would be accurate.
Do you guys try and set a limit on your number of beam sizes and header sizes? Like, do you ever upsize a little bit more than you normally would, just so that you don't have
Yes.
150 different?
Yes,
beams?
different weights of members.
Yeah.
Yeah. Yeah, like 12 by 26s or 18 by 35s or 24 by 68s, like if you can like stay with, you know, if
A
you
lot of
jump
times
to
what
a
happens
depth.
is You jump to the next biggest size, just because otherwise you have a beam and header schedule that's like 2 pages long.
Yeah, you try and
the
you
erection drawings
smooth
are more
out.
Complex.
Yeah.
It just becomes, you save money in construction even if you're like going a lot conservative. Or
Yeah,
really conservative on your gravity.
The steel fabricator doesn't have to order in like 60 different member sizes. They could go to the shelf for the common ones, right? 14 by 22s, 16 by 36s, stuff like that. So.
There was a time,
Yeah, how many pages was the shop drawings on?
Oh, hundreds, yeah, hundreds.
there was a time within the last like 2 months where I think 2x12s were cheaper than 2x6s, like significantly.
Oh, really?
Yeah,
Because
which
that
was
would-
insane.
Wow.
Maybe it was 2x10s, but it was like.
And so then they
way
came to-
harder to get 2x6s, so people were framing with 2x10s for like a couple months there.
Wow. So on top of this, right, on the post-processing side, a lot of programs have modules or like integrate like various designs beyond like going through and stepping to the next level, right? Now that we know displacements and forces, we can actually design things. Well, like visual analysis, they've got quick footing, quick connect, there's Norm, right? So they have a bunch of different software programs that allow you to design more like individual elements, right? If you wanted to design the foundation by hand and you could, you know, collect all the information, all the loading, and you just wanted to look at the footing, well, you can just buy Visual Foundation, right? And you don't need the entire visual analysis, you know, software package. Shape Builder, that's also a big benefit, like AE Dynamics, which is a structural engineering firm in town. They do a lot of curtain wall design, so like extruded aluminum stuff. If you look at the front of Norm, like the big windows in Inspiration Hall, right, they're actually structural, like the mullions that are sitting there, right, the horizontal and vertical members that are in those windows, they actually carry the glass, right? They wind pressure on the glass. And so you have to analyze those, right? There's somebody out there. So they look at these crazy, complex, extruded shapes, and then they put wind pressures on them and they analyze it. So Shape Builders allows you to build these crazy shapes, composite members, and then you can put them into VA and then design them like you normally would, right? Which is pretty cool, right? Concrete section, concrete bending, retaining walls, VA Connect, that's pretty cool. So like for Norm Asbjornson Hall, you can do a gravity model, it designs everything, then you can say, you can create connections at the end of every member, and then you can pump it out to this VA Connect, and then VA Connect goes through and it says, okay, it's a shear tab, give me some designs for what your shear tabs are based on the depths of your member, and then it goes through and it just scans everything, looks at all the demands, and then it'll check every connection for you.
Did you do that?
No. In general, what'll end up happening is like the tables in AISC 360 for typical shear tab. Once I don't have the numbers in my head now, but when you're doing it a lot, like there's some numbers that kind of stick in your head for like what a 3-bolt connection can do, 4-bolt, 5-bolt, 6-bolt, and then you look at those members, right? Whether it's W12s and then 14 and 16 and then 18, like all those are so you look at what's the max reaction. If that one is okay, then all the other ones are okay. Because like Aaron said, we do that a lot, right? We're not going to make a specific connection for every single beam to match the exact design, right? We're going to smooth it out, okay? And so when we smooth it out, a lot of times you just check the worst case. If it's in trouble, then you start, scaling back, and maybe like you create, a deviation in the design that certain members get maybe a double angle connection down to a certain point, and then from there you use the typical shear tab. So,
How much more expensive is like each of these packages?
I don't know.
I'm assuming just like VA is the most expensive.
Cause their advanced just has $4 signs.
Oh, buy. Here we go. Buy. VA Suite. So you get VA Advanced, Visual Foundation, Shape Builder, and I'm not sure what VX is. So that's $2,300 a year. Whereas some of the other ones, like just Shape Builder, is $345 a year. I mean, not crazy, but I mean, you can do a lot of things by hand, right? A lot of things by hand. So, I mean, do you really need VA? Maybe not. I mean, if you're like working with an architect and you're just designing houses, you probably get away with not doing it. Right?
Got Madison coding on your team.
Yeah. RAM, same thing, right? They have RAM structural system. Well, they have RAM connection. I mean, do you guys have some of these stuff for packages, right?
Yeah.
So again, the integration between this overall finite element analysis software, and then it allows you to do other things. RAM Concept. There's one that does like just concrete. Just concrete design. RISA, this is for you, Sutton, right? This is your baby here. Which one of these do you use?
I use 3D and floor a lot. But
Woo!
I've been using Connection quite a bit too.
Wow!
They do seismic detailing, so.
Man. So they'll like detail out a brace frame connection for you?
Yeah, if you got it's pretty sweet.
No
If you gotta do
way.
a seismic E, like special concentric brace frame or
Yeah.
something, you go through.
What a
all
fucking
the
pain in
seismic.
the
Yeah,
ass. Have you guys done that in steel design yet?
Just getting to it, kinda.
Are you guys?
Trying.
Trying to teach them.
It is impressive, like all of the design checks you have to go through, right? Pretty.
I don't think we're gonna get to that point.
You've got a lot going on when you look at, you've got this brace coming in and special concentric brace frames. You have to use the actual strength of the brace. And on top of that, you actually add to that this factor called RY, which takes into account the fact that when you make this piece of steel, it's actually stronger than it really is, right? RY, have you guys talked about RY?
Yeah.
So RYFYAG, it destroys you. It destroys you everywhere.
Seems so simple.
It is very simple.
But there's checks on his spots.
But you have to check so many spots in different configuration, right? And like obviously like bracing bays get longer and shorter, which changes your angles, right? Which then if you start having this RYFYAG, which is like, I mean, you can have 500 kips coming out of like a 6x6 brace, right? So 500,000 pounds you're trying to pull on this steel gusset plate, right? And then there's like all these different analysis methods you have to do. I mean, you used to have to like, for column design, for steel concentric brace frames, do a model in which all of the braces in compression, like you could not have any braces in compression. So then you'd have to go through in VA, click all your braces, like push your building in one direction.
Braces and-
Well, you push your building in one direction and then make sure that all the braces that would be in compression no longer were two-way members, but one-way members, so that they would no longer carry any force in compression. And then you would design all your columns.
Just with the tension.
Yeah, tension would just, you like push it,
Then you need-
and then you push it the other direction.
And you just design them so they buckle?
So, well, yeah, so like, that's another energy dissipation means in a special concentric brace frame, right, is the fact that the beam buckles.
Plastic mold.
Yeah, so then it like creates a hinge in this brace, and so you use 0.3, right, 30% of the buckling capacity of the brace, right, all that stuff. It's fucking cool, right?
We're getting to it.
Good.
I'm actually,
Alright, well, you guys can just all punt and
Trying to
be
use
like
stuff.
Sutton and just use the easy connection, and then you just like,
I'm
I don't know what I'm doing. Do one by hand, Sutton, huh? Have you done one by hand?
That's what I'm working through. I'm doing one by hand right now, and then I'm going through recent connection.
Yeah.
Seeing like all their comp lists.
Oh, good, good.
But
I
It's
think
brutal.
it is.
It's, I mean, like, it's like 70, 60 pages or whatever. dude.
It's
Long.
intense.
Yeah.
It's intense. But the seismic manual, I'm sure Damon has showed you, right? They have pretty good examples. And actually, if you go out to the AISC's website, you can actually get even more examples.
design guides.
Yep, and then there's design guides. Okay, there's all sorts of stuff out there. Once you do one though, that becomes your example for every building you do from then on. Seriously. Until the code changes, and then you throw it away and you do it again. All right, so they have all these different software programs, right, that integrate to other, more intense detailing or design, right? RAM, Brisa. There's ones like eTabs where it'll actually like go through and you take VA model, you pump it out to that connection, and then it actually details it. So you could like have all your details in there, and then it'll say, okay, we need to change this. It changes it, pushes it out, and then and like some shops that actually do design and fabrication, right? That would be huge to be able to just like put it in the thing. It goes, it grabs the connection that you need at that point, pumps it out to a drafting software program, and then you can print it off, and then you can make it. So it's fucking sweet. And like I said, it's almost required for today at some level when you get into the complex of geometry, right? Curves, acute angles, tapers, complex loading, right? It just keeps getting harder and harder. I mean, honestly, I haven't been doing it for very long, but I remember ASCE 705 was the book that I started with. And I mean, it was like this big. Now we have two books that are about that size, right? One's just the provisions and the other one's the commentary. It used to all be in one book, right? The steel manual, it's changed a lot. I started with the black one, which was before the maroon, which is now teal. And in the black one, designing special concentric brace frames was fucking easy compared to now. Seriously, right? They've changed it drastically. And before that, I wish I was there before that, because the black book was the first time that you really had to do anything. Before that, it was a Wild West. You honestly could call, like, I looked at old drawings we did at Morrison Merrily for houses up in the Yellowstone Club that use a lot of moment frames because they got big windows and stuff, right? And they would have called it a special special moment frame. In no way in hell is it a special moment frame in today's standards, right? I mean, the College of Business building, when I first started at Morrison Merrily, when it was done, the code changed, and all the braces in the College of Business building are no longer seismically compact. You couldn't use them. You could not design the same special concentric brace frames that we have in the College of Business building on campus right now with today's code. It's non-compliant.
But it was fine with.
It was fine at the day and age, at the code that we used, right? They changed the seismic compactness requirements for braces, which, have you guys dealt with those yet? It's kind of nice, in the seismic manual, give you this nice little table, right, Sutton, that tells you can select which brace, maybe gives you a little dot. And it's mindless work.
Nobody checks unless something bad happens, right? Like you.
Well, no, I mean, it's
like, there's nobody like checking to make sure you've done it. It's like kind of on you, and like you really could just use your old. If you're like, oh, That was fine back in the '90s when we did
People
it
do
way.
that.
You could just do
People
that,
do
right?
that,
People
Elias.
do that,
Yeah.
and they're just like, well, I know it's not gonna.
There was a project manager at Morrison, Maryland, I'm not gonna name names, but they, I had a very, very, very hard time with that individual because they used the green ASD steel design book.
What is that?
That is like 5 code cycles about. That's like the book that they started using. And that's how they were designing things.
Well,
I could see.
And so then you go in there and like as a project engineer, maybe you guys who have been working have had this problem, right? I started having it a lot because you'd step in and say, hey, by the way, we have to design this brace connection for RYFYAG. And when we do that, this connection gets massive, right? Things get huge, welds get larger, columns get bigger, like all of these things, right? And they're like, I've done this 30 million times and this is the size that I always use. This is what we're gonna use. Or one of the biggest concepts, and I'm gonna try and instill this into you guys, is when you're designing special concentric brace frames, Damon has told you, right, the brace is the fuse, right? The brace is the fuse. It's supposed to turn into a piece of spaghetti. We're gonna stretch that steel till it yields, right? Then we're gonna turn around and we're gonna push it until it buckles. We're gonna do that multiple times. And that thing, right, the fact that that thing is stretching and buckling is the whole premise behind the fact that you can use an R of 6.5, right, or 6 1/4, whatever it is, depending on whether it's a framing, whatever, bearing system or a frame system, right? That whole premise of R, using that R, is the fact that that brace gets bucked, right? And it dissipates a lot of energy. In order to do that, the rest of the system has to be able to handle that brace doing that, and that's why you do RYFYAG, because you cannot have a link in that system, a connection, a beam, a column, a connection to a footing, that pops the second you get to RYFYAG, or pops before that happens, right? You're screwed, okay? And so when you design braces, at every level, the unity on your braces should be like fucking dialed. Like you do not want to add, like you don't want a brace that's at 50% unity, right? Because when you hit it with that earthquake, it's never gonna yield, right? So what does that mean? That everything else in your whole system is going to have more load on it because you're not going to dissipate any energy until something yields, right? And so I've designed buildings where it's like everything is gnat's ass, and even the steel erectors were like, holy shit, these braces are tiny. Because there's a misconception, I mean not a misconception, but just an old school way of thinking of that, oh, I'm just gonna do a 5x5 by 5/16 brace, and I'm gonna do it at every level in every brace frame. And I don't care what the unity value is. We can design it for the worst case down over here. We can design all the connections the same. Well, what that does is that changes the behavior of the entire building. And now those foundations that you designed for an R of 6, right, and you reduced your demand, right, your seismic demand by 6, right, are not going to see that demand. They're going to see a demand that's a lot higher than that, right?
So like you come up with your earthquake loads, but then when you're doing some of those special detailing, you have to do your capacity limited design.
Yep.
And which is usually much higher loads than
Much
like
higher
an
loads.
earthquake. So like what you just said, how does that happen in the real world? That's what I was kind of wondering when I was working through it. I was like, okay.
Well, so
Even
you
with my seismic load case, but
Yep.
it's like nothing compared to my capacity limited design. So like
but see
if it was a
you
real earthquake and it was close to my loads, then
But
it
you're-
wouldn't be yielding.
yeah, but you're designing the braces for that earthquake load.
Yeah, but then, oh, yeah, okay.
And so the braces are what then see that earthquake load, and then beyond, like at that point, they should be yielding, right? They should be starting to dissipate energy. And then from there, what they're saying is that everything else in your system has to be able to handle that brace doing that. Right?
Yeah. I would, yeah.
So then that's how that energy dissipation, it's like a fuse, right? You're gonna push, and then the first thing that reaches its limit better be those braces. Or better be that plastic hinge in your moment frame, right? In your beam. It better not be in the column, it better be in the beam, right? Strong column, weak beam, sort of thing. Right?
Ordinary, just stay ordinary.
Or you can just do ordinary. But that might be how your thing behaves if you design your braces for a unity of 0.5, right? Because then because the demands you do for ordinary, right, an R of like 3,
Yeah.
right, are twice that of the special concentric brace frame.
Yeah.
And so then when you start pushing, the braces don't yield, all of a sudden, whatever is the weakest link, that thing's gonna start, getting destroyed, right? And so try taking that concept to some of the people that are using the Green Book, or some of the people that designed moment frames, you know, iterations ago, and they're like, you're crazy, right? It takes more time for you, for, you know, all of you guys to sit there and run all these calculations. So like, shit, you ran out of budget? Like, I didn't budget for this. I'm like, well, not my problem. Like, this is what it takes to keep this thing standing, and this is the code that we live in. And so it was tough, especially going from the Black Book to the Maroon Book. There were some big steps in that jump.
I can see that though, like I'm attached to my little teal book, like I like it.
Yeah.
It's a new one, I'm gonna be
Starting to learn the
sad.
way. Yep.
It's gonna be sad.
You get excited.
You get-
Especially you like start
excited.
tabbing it, and like
Okay.
mine, the cover fell off because because it's well used. It's
Or
like
David's,
it's like a,
pages are falling out.
yeah, it's like a, it's like a, reputation thing. It's like, look at this, man, I fucking use
Part of
this,
that.
right? So anyway, all right. So the governing codes kind of make it, right, in the teal book, the sizing manual, if Damon gets to it, when you load up brace frames, they give you an analysis, they give you a list. You gotta look at the capacity dependent loads, but also they give you things where, you gotta look at what's the resistance to the building to overturn, right? Could it just overturn? That would limit your ability to actually push on the system. Also, you can do nonlinear analysis of your buildings now. They let you do that as well. Okay, so all these governing codes can affect what things you use, right? ACI 318, if you're doing special concrete shear walls, right? You got to look at cracked section modulus, right? Concrete cracks, right? So when you like push this concrete wall over, it's going to crack, and cracking it is going to reduce its stiffness. And you got to incorporate that, right? So in VA, it's easier to incorporate some of those cracked section modulus and properties than it might be then to chase all that shit by hand. As you guys noticed in the exam, right? Other industries that use this, aerospace, hydrology, hydraulics, electronics, everything, right? It's everywhere. Finite element analysis is everywhere. Where did I put it? Oh, okay. So that's FEA in industry, plus a little bit about brace frames. Just because I love steel so much. I'm not super. You get to teach concrete. You get to teach 2 classes of concrete next semester.
And then one the semester after that.
And then another one the semester after that. Yeah. So much fun.
Be prepared for people.
Concrete.
Concrete one with Damon.
It is concrete 1 next
No,
semester.
I'm saying be prepared.
Oh, because you're not gonna take you're gonna take the second?
Yeah.
Man, you might just wanna survey the class next semester. You can do that, I'll let you come in, I'll even print out extra handouts for you.
Okay.
Are you sure? Okay. You guys all heard it, I gave him the opportunity. Gave him the opportunity. All right.
I'll have other stuff for us.
Model and discretizing, right? What are we trying to do overall as a structural engineer?
Represent structure.
We're going to represent the structure. And which structure are we representing? Trying to represent. Ultimately. The real world. Thank you, Madison. And really, are we going to match the real world? No, we're going to approximate the response. I guess I could zoom in. Wow. Of a real world problem. Right? We're going to approximate the response of a real world problem. Emphasis on the approximate, right? When we build an FEA model, what does that model represent?
A mathematical representation.
We're representing our mathematical model, right? Our best representation, or really an approximation. Again, approximation. Of our,
We can get like within many decimals of exact of the mathematical.
in some cases, yeah.
It's like pretty
Certain.
much exact, like if you're going to like 6 decimals of like the mathematical model, that's like,
But I mean,
it's pretty exact.
Yeah. I see what you're saying. But when we're doing it in structural engineering, right, there's a lot more than, say, our individual cantilever, right? Or our
Like thinking of
individual.
the cantilever in this one, like it's like
What's that?
Like this homework.
Yeah.
It's like pretty money.
Yes, money, right? But a lot of what we do is not that simplified, right? We wouldn't use, I guess if I was designing a cantilever, I probably wouldn't even put in VA to do that, right? Yes, Aaron?
For the hand calcs, can we just, I mean, you don't want like a code or anything.
Impress me.
We can't just use like.
Impress me.
We can't use like the cantilever tables,
Don't tell.
What's that?
like the tables in the steel mill.
Oh, yeah.
You don't want like.
No, you don't have to derive it.
undeveloped
No,
code or
no,
something.
no.
Okay.
You don't have to like solve for the equation for the deflection of a cantilever based on integrating the moments,
Use
the
some
equation for the moment.
mechanics, and then
What's that?
Use some mechanics for the forces and moments, and then use the steel manual for deflections.
Yes.
I mean, the manual also has the
Yeah.
shear and the moment too. If you want.
It'd just be two separate cases.
Wow, if you're looking at that for that, then you've got problems. You've got problems.
You gotta have a source, you know? Like,
Well, I understand there's a source there,
Your
but
source is
like,
general
I
mechanics.
mean,
I'm just saying.
I know,
It's gotta come from somewhere.
I understand that. Don't lose touch with everything and just start looking everything up. I know as engineers, we try and simplify stuff as best we can because we're lazy, but. All right, so our approximation of our mathematical model is our FEA model, right? And we need to take the real world, right? And our first step is develop this mathematical model. In this thing, we want to capture our behavior of interest. Right? And more importantly, we want to capture that behavior of interest to an acceptable level of accuracy without making the model too complicated. We want to do it just right? But there's a lot of subjectivism in that, right? What's acceptable, right? What is our behavior of interest, right? What is too complicated? All of those things. Right? Well, in order to do that, we make a lot of simplifications. First of which is we generally simplify loading quite a bit. An example of this would be like you were talking about, Sutton, with seismic loads, right? We might take our story shear, which most of you guys have gone through Mike's class. Is that a true statement?
No,
Oh, man.
next semester.
Right? We might take story shear from earthquake or wind and apply at a point in the diaphragm versus a pressure on a wall versus line load on the edge of the diaphragm right? Maybe see the differences in those and how that might trickle into our design. Okay, for those of you who haven't taken Mike's class, right? Earthquake loading is all based on mass, right? So the load source is the mass of your element, right? For your structure. And so it's going to change, right? Wind is all based on projected area, right? It's coming from the outside. So there's two big differences in the load sources of those two loads, right? But both of those, we could get a story shear, right? Tributary area above and below a diaphragm. We put it into, say, the floor above us, right? How do we want to put it in the floor above us? Well, do we want to model the wall? Well, if we model the wall, we might want to put load on that wall, right? For modeling a column, maybe we say we have girts that span to a column, and then we want to put a line load on the column, and then that column spans to the roof, right? And then the roof takes the load from there. If we didn't give a shit about what's going on in the wall, we just wanted to design the diaphragm, maybe we just put a line load on the edge of the diaphragm, right? There's a lot of decisions to make when you go and you say, okay, this is the real world, I'm looking at Roberts Hall, what am I trying to design out of it? What is this mathematical model or simplification of the real world I'm gonna do? All based on the fact that I'm gonna go design the diaphragm, or I'm gonna design the girts, or I'm gonna design the column, right? Alright, I think that's it, huh? Damn
Two
it.
over.
Aaron's getting really good about making me deviate.